get started here. Is it working? Yep, it's working. Okay. So we're going to start out with what is the need for what we're talking about. The quantum mechanics is really where we're headed, but before this, in the early 1900s, you know, and on up to that point, everybody was hunky-dory with physics. I mean, you could have they're developing some electricity. They were playing around with a lot of measurements and science, and they thought they really were having a good idea of how things were working. And then some funky things started happening. And if you take any object, like here's a light bulb, I don't know if you can see inside, but there's a metal filament, right? So it doesn't have to be a metal filament. It could be anything. You could take a hunk of bone. It doesn't really matter. As long as you heat any object up, it just starts glowing. You can't stop it. That's nature. And the hotter you heat it, right, the more intense the light becomes and stuff, but it also becomes in a shorter wavelength, higher energy. So maybe I've played with, going camping, you can't help but play with a little campfire and all little coals and things, right? So I don't know if you've noticed, but you know, when the fire's gone down and there's no fire there at all, but you're kind of jamming the stick in there, sometimes you can find a deep red coal, right? They're kind of glowing deep red, but they're not bright orange, right? They're this deep red. But if you remember back in the middle of the night, you know, you had this broad fire going and you're dinking around with the coals on the bottom, right? It's much brighter orange, right, down there. So see how it's much hotter then. At night when the fire's gone down, it's cooled, but it's still glowing. These objects. It doesn't have to be wood either. It could have been anything that you burned, and it's going to be glowing. So that's pretty much what black body radiation is, but that's really not a good enough definition for these physicists. What they want, this is how they picture a black body. I lost my flashlight, so I'm going to have to use my phone. Whoa. Yeah, I do too. What? Isn't that weird? It doesn't turn off. Oh, there it goes. Okay. Let's turn on the flashlight here. I know, isn't that a cool button? All right. So black body radiation is black body radiation, but it doesn't really fit the definition that the physicists want. They want this light to be equilibrated. In other words, it's inside this perfect reflector, and then I don't know if you can even see it, but there's a pinhole in here. And if it's a really dark room, you'd see the light coming out, a little tiny pinhole of light. That officially, to meet all specs, is black body radiation. Okay. So why are we even talking? It doesn't have to be, because remember light, that electromagnetic spectrum, oh, we kind of skipped that, didn't we? The electromagnetic spectrum in here, let me blow this up. When you say visible, I wish they'd left this part off, because it makes the plot more confusing. That's exactly what you're saying. This is visible light, right? Roy G. Biv. So it could be any radiation. So you take any object and it's going to be glowing. Like you and I are emitting heat right now, right? But if I would take Pablo and, I don't know, put him on a stick and just heat the crud out of him, he'd die, of course, but he would start glowing just like any other object, a pencil, a piece of chalk, whatever. It doesn't matter what that object is. It's just going to start glowing. And this is what they were measuring, and they're playing around with, right? So don't see these Roy G. Biv colors. Try not to look at that. That's not part of the plot. They're just trying to say that the shorter the wavelength, here's a little peak. And that peak, it shifts this direction, right, to shorter wavelengths as you increase the temperature. That's the point we're trying to get across. And that there is a peak to it, right? It starts out, there's nothing, you don't see much. And these are, in only the only visible region is right here. So you really got to heat the crud out of something to really get it to start glowing that you can see. Okay. But what's kind of neat is it's kind of goes up, but it has a peak and it drops down. Okay. I don't want to skip anything here.
Okay, so this is wavelength versus energy distribution, right?
Yeah, and they say distribution because it's not one single wavelength. Right? It's a band of wavelengths with a peak. And that peak just shifts to shorter wavelengths as you heat stuff up, as you make it hotter and hotter and hotter. And my little computer animation crashed, so I can't show it to you. But it's pretty much the same as this. As I would crank up a higher temperature, you'd just see a peak that's bumped up higher and shift that way as you crank up the temperature. Okay. But it'd be kind of nice because then you wouldn't see this band of colors.
So, as waves move through time, do they, like an ocean wave, can they just spread out on their own and increase their wavelength?
So time is going to be an interesting factor. Time really complicates things. A lot of things that we're going to be talking about are time independent. And we're just going to be talking about a moment in time, what are the possible energies, what are the possible states, and what are the possible outcomes. When you incorporate time into it, I think to answer your question,
This is the same
if you
black body radiation that we're talking about in like astronomy when we talk about explaining whether the universe is expanding or not. Bell laboratories came up with that radar that identified black body radiation way out.
so, well, directly what you're talking about with black body radiation, yeah, all these stars, black body radiators. So if you look at their spectrum, you can pretty much get an idea of what their temperature is, and by their temperature, get an idea of how old they are, that sort of thing. But when you're talking about expanding the galaxy, that's redshift. So these wavelengths, and this is the only way they know with it, they expect it to be right here, but it's all shifted to the red. So that means that object has to be going away from you. So, yeah, and no matter where you look, right, everything's going away. So that leads to that whole Big Bang theory. It's kind of, I've always thought of, we're getting off topic, but I've always thought of that as kind of caveman thinking, because we always think of things blowing up. That's all we can imagine. Why isn't there another idea, right, of things just being a singularity and then blowing up? At 0.02 microseconds, all of a sudden there's helium in the universe, and they have it timed out every millisecond if you watch the movies and read the literature. It's kind of odd, but you'd think there'd be some other idea besides boom. Right? I don't know.
There's that one that says we could be in a state of constant contraction and expansion. So we move out. And then
Oh yeah. They don't. Yeah. Okay, so this is all black bodies. Take a pencil, heat it up, it glows. That's the thinking. That's the idea there. And then we have this Wien displacement law, right? This is how you can get that lambda max. Because they measure these things, and they're starting to make some measurements and trying to figure out some predictions. And so that's the temperature and the maximum wavelength. And this little constant is called the second radiation constant. And I always look at this, and I think cm. It's just centimeters. It's not speed, because what's the little symbol for speed of light? Little c. So I always look at that. I want to take 1.44 times the speed. No, cm is just centimeters. So this is just a constant. It's just a number, like the gas constant, big R. It's got a number with units. That's all this thing has. The second radiation constant is 1.44 centimeters times Kelvin. It's kind of odd, but that's how it is. Okay. Total, again, all this about this plot of how the energy is distributed over wavelength as you heat objects up. Total energy density. It's just like any density. It has this funky little symbol, epsilon. I'm not so good at drawing it, but it's epsilon. Just like any density per unit volume. So you take the energy, divide it by the volume, and you'll have energy density. The Stefan Boltzmann law. I didn't write it here, but that's supposed to be the same little epsilon. Just another way of writing it and showing how important temperature is. That temperature amplifies itself. It's temperature to the fourth power. Okay. So Stefan was kind of, this is all kind of follows history. So Boltzmann got his name on this because he figured out this part with excitants. So I don't think this is important for you to know, but it's just kind of one thing led to another, right? But excitants is going to be in your, I saw some of this in your homework coming up. So excitants is power emitted per unit area. Now, Pablo, the units for area were what? No, meter. So stick in the standard metric units for everything. So it was meter squared. How about power, though? Standard metric unit for power. Ooh, that's even more helpful than the answer I was expecting. Joules over seconds. We're supposed to say big W, which stands for watts, right? Yeah, it's going to be really helpful for you to remember joules per unit second. So power can be emitted, energy emitted per unit second, or it could, because that's producing energy. So power can be produced. Power can also be consumed, right? So you're consuming so much energy per unit second. In this case, we're emitting it, right? It's power per unit area. Okay. So what's the problem? What's the big deal here? Well, with everything they had, has to do a lot with heat capacities of solids. It was just, for example, one of their, what was it? I think it was, this is one of their ideas in physics. They said that these solids, these heat capacities for solids at constant volume had to be 3 times the gas constant. And everything's working great. This is just one of the little, when you solve any big complicated problem, there's always a lot of little pieces of the puzzle that go in. And this is one of the little pieces. And what I'm just driving at is that for them to try to model what's going on here, because they have these plots, right? The nice green one, they have that plot. And they knew that the wavelength was increasing and then coming down. They plotted it out. But when they try to calculate it and simulate it, this is what they get. It goes straight up, and it doesn't stop. And it has some real problems. I mean, just imagine, I mean, to me, it would just throw a curveball, and all you're thinking, you'd be pretty freaky. I mean, you're from baseball to riding bikes to candles to your whole life. You think you understand it. And then something like this happens, and you're going to get freaked out because what does it say? It says that according to what we understand, we predict that this is at room temp, and okay, it should be glowing in the dark. It's not glowing in the dark, right? If you heated this up a little bit, just a little tiny bit off of room temperature, I'm going to get a sunburn from it. And it's just infinite energy has always been given off. So in other words, our ideas of physics and things are astronomically off. So they called it the Rayleigh-Jeans formula, right? I guess they're happy about something because it matched at way over here, it matched a little bit, so I guess they must have been somewhat proud of it, right? But it just blew up on you. And they call it the ultraviolet catastrophe. That is just, we've got some problems there.
So the ultraviolet catastrophe is a difference
Because
between
remember,
shades and a steam and
well, where's ultraviolet? It's going to be really short wavelength. So look at this plot, it just blows up, goes to infinity. So at really short wavelengths. So that's why they call it the ultraviolet catastrophe, because these short wavelengths are just shot up. So it's kind of neat. This is the time of Einstein. So good problem. So he works on it. And from what I've read, that he was pretty close, but his problem was that he assumed that this object, the solid that you're trying to make glow, and you're heating it up, all these, what it's made up of, all these components are all oscillating at the same frequency. Well, that's wrong. So then this guy by, I think it's Debye, D-E-B-Y-E, he came in. Where is this? Right? Well, I'm not sure if it's even in here. And then, yeah, I guess we're okay. Right in here. His name's not in here yet, but it goes that these objects actually oscillate over a range of frequencies, and that solved the problem. But just by Einstein saying that it oscillated at a frequency, he's saying that, man, these particles, they can't take on all possible energies. They can only take on certain energies. Quantization of energy, huge step. That these molecules can't take on any energy. That's a whole different way of thinking. That's like saying, I'm going to throw this pencil to Pablo, but I can only give it certain speeds. Can you remember the equation for kinetic energy, 1/2 mv squared? Well, this thing can only have certain energies, this energy or this one or this one. So I can only throw it to him at 5 miles an hour or 10 miles an hour or maybe 15. That's it, nothing in between. Well, that's ridiculous, right? So for us, but not for, when you get into this microscopic world, the physics works. If you quantize energy, okay? So here's some ideas for quantized energy, right? That these particles can only have certain energies. Right? And if you're dropped from one energy state to another energy state, they're trying to show that a photon of light can be given off. And in this case, they're illustrating a photon of light by a never-ending wave instead of like a packet of, like a bullet packet of energy. So this would be called, on this jumping ahead, would this be emission or absorption? Yeah, emission. Right? Same with this one. So it could jump down from one state or whatever state. Okay. So the energy of that photon will just be the energy difference in the states. Okay. But I think that energy E equals h nu. We had this in the concept preview. Right? So h was Planck's constant. Okay. So we talked about cm as centimeters.
Was that equals hc over
Lambda, remember, from the concept preview. So by using this Debye formula, right, they got it to work. Okay, they got there. Here's the, I don't know if you can see it very well, but that's that Rayleigh-Jeans law. That's the one that's not working. But then they finally got it to match up. If you take into account these range of frequencies they can oscillate into from some, oh, there's Debye's name, from some minimum to some maximum wavelength, the Debye wavelength or frequency. Okay. Well, I don't really have much to say about some of this stuff. I just copied down all those. I want to jump down to wave-particle duality. There was a movie. Gosh, I bet it's on YouTube to get some parts from this. Because there's certain classical movies that everybody should watch. This is one of them. And I forget what the heck I think it was called Scanners or something. But this guy, he figured out the Broglie wavelength of different people's heads. And he would call them. And he would transmit that de Broglie wavelength, frequency, through the phone. And they would listen to it. Their head would start oscillating. Now, they never once used the word de Broglie in there. But I thought it was one of the neatest shows because it really, really works.
what was it called?
I don't remember. I want to say Scanners, but I'm not sure that's right. It's an old black and white show. But you may have seen this in some videos. Let's see if I can find it. The Tacoma Bridge. Did you ever hear of the Tacoma Bridge? Okay. So what they're trying to say, de Broglie just says everything. You can't stop it. Everything has a wave property to it. So that means if you apply that energy, that de Broglie wavelength, and get the energy, because remember, E equals h nu, E equals hc over lambda. So every energy has a wavelength, right? Every wavelength has an energy, whatever you want to think about it. So I have an energy. Match my energy with my de Broglie wavelength, I'm going to start oscillating. I'm going to start resonating with that energy. I'm going to start absorbing it, right? And I'm just going to start resonating at that. See, I can't see, how am I doing it? It's almost like a spring, right? A spring. You can pull it down. I didn't bring one. But if you pull a spring down with a weight, does it change frequency?
Yeah.
I used to think it did until I sat there and counted it. It
I
doesn't.
see what you're saying.
All it does is it
Remember
changes
that
amplitude.
demonstrations.
All it does is change amplitude.
Yeah.
It doesn't change frequency. So it just has to go even faster in the center, right? Because that's harmonic motion. It's changing speed the whole time. So I can't move my hand in harmonic motion, but imagine a spring going up and down. So all you do, if I apply the de Broglie wavelength to a spring, it's just like pulling it down more. So it oscillates even at a larger amplitude. So I'm oscillating right now at my de Broglie wavelength. You can't see it because it's so tiny. The Tacoma Bridge, any object, automobiles, they're all oscillating at their de Broglie wavelength. Well, if you can get the winds and get everything right to get this thing start oscillating, everything has to be exact. Add its de Broglie wavelength, it's going to start resonating. And you can actually see that this object has a de Broglie wavelength. Where did it go? Oh, there it is. All right. I don't know how the thing could even stay together. It had to have fell apart.
Oh yeah, it did. It ended up collapsing. There's several bridges that did that.
Now, do you? What I wonder is sometimes I've packed a lot of trucks I've moved, and some stuff is really heavy, and it's just there's no way this bloody thing can move. But if you're going down the road, if you hit the right bumps, right? I don't know. It seems like maybe that's a de Broglie wavelength thing. I don't have to Google it and find out, right? Is that how these big objects can move in the back of your vehicle? I don't know if you ever noticed this before, but seemingly I don't know how these big ass things move, but they do, and it could be the road, but that's. And if the Tacoma Bridge can do it, why not a box in the back of a pickup? But okay. Photoelectric effect. We don't have. Oh, here's a de Broglie. Yeah, there's our de Broglie wave. I always kind of skip photoelectric effect.
Now, does
But
the Broglie, does it continue to increase in, I guess, frequency since the amplitude does, but the amplitude will change, right?
only the amplitude change. The frequency can't change.
So the frequency stays the same.
Yeah.
Will the amplitude
Because
continue to
I think the idea is energy is quantized. So you're in this one energy state. So if you're in that one energy state, you match that energy with the de Broglie wavelength for objects. So it's one of the very few instances, they argue, this is one of the very few instances where you can actually see microscopic properties in the macroscopic world. It's very, very rare that you can actually see these things, that they correlate.
So you have to constantly be increasing. You have to constantly be applying energy in order to
Yeah.
get the
So-
amplitude to continue to oscillate.
So I think if you had some kind of wavelength emitter, and if I'm walking across this room, then and if you somehow apply that to me, I'm going to start oscillating. You're going to start seeing me, I don't know, I guess, coming off the floor and getting, I don't know, maybe I'd look like the Tacoma Bridge or something, right?
Sounds gonna be scary.
But what is P? And where did that,
Isn't that, it's not Planck's constant.
no, Planck's constant is little h. Where did it go?
We're looking more downstream.
My de Broglie, there it is, my de Broglie wavelength relation. What is little p? It's linear momentum, which is what times what?
M's
M-
speed, M-
No, that's kinetic energy. MV, just MV. Mass times speed is momentum. So the Broglie wavelength is related to momentum. Okay, this is another demo that crashed, so I just have to do hand waving. If I, the photoelectric effect. Oh, instrumental. You had instrumental, right?
Yeah.
All right.
And
So please explain the photoelectric effect to us. What instrument, what detector was it used in? You're an instrumental now, right?
Yeah.
Yeah, you haven't had it yet.
No, but I thought that's what measuring the atomic.
The detector. You're talking about an instrument. I just wanted a detector. Had 3 letters in it. Started with a P. M. Gosh.
They should take a guess.
T. PMT. Don't you remember PMT? Photo multiplier tube. And you had to draw, you had to sketch it and everything.
Yeah.
Right? So, jeez.
It looked like this. He had like something like this or whatever, and then he had like
Ooh, there
something
we
like
go.
this, and then like this.
Oh, yeah. I remember because I got that one wrong.
He had a, yeah, he's drawing a cascade of electrons.
Yeah.
Right?
The electrons are,
And it all started at the top. Good.
Yeah, something up here. I don't know. It's something about like the colder it is, the
Good.
less interference
Good.
you get.
So at the very top is this photoemissive material, right? So from one photon, you can get, because the electrons are current, so you can get a nice current. But it all works on the photoelectric effect. So if you have a solid, let's say a solid surface.
Yeah, it's like when radiation hits metal, right?
Yeah,
It's like-
you're going to shine radiation on metal. So let's shine red light on here, a whole lot of it, all right? Make it really intense, all right? And no electrons get kicked out. Because the point is work function. Every metal has a work function. If you apply this minimal amount of energy, you can actually kick out an electron, okay? So this is another idea that probably helped Einstein think about quantization of energy. But so it doesn't matter the intensity of that red light, you won't kick out any electrons because the work function must be a little bit higher than red. Let's say that the work function exactly corresponds, that energy exactly corresponds to, I don't know, purple. Remember all these had a, oh, let's pick one that we know the wavelength of. Violet. Remember in the concept preview, we said red was around 700, I think, and violet was around 400 and something. It was shorter, higher energy. So let's say violet is where you can finally get electron get kicked out. So you can shine red light, a laser of red light. It doesn't matter because each individual packet of red light is only corresponds to 700 nanometers. And you can calculate the energy equals hc over lambda in joules if you'd like, but the same thinking. So 700 nanometers is enough. 500 nanometers is enough. You got to keep getting shorter and shorter and shorter. You shine one photon of violet light, you'll kick out an electron. You shine a laser of violet light, oh, you can get a lot of electrons, right? But the point is intensity doesn't matter if you haven't reached the work function energy. Okay. So when they start talking about the photoelectric effect, they're saying just this. Here's the energy of the photon, right? And you remember E equals h nu. Well, that has to be the sum of two things. It has to be the sum of, first you got to kick that electron out, that energy, plus the energy remaining. It goes into the, I should blow it up. Well, I could write it here. H nu equals a fancy work function symbol plus 1/2 mv squared. M of what? What's M? Mass. What's 1/2 mv squared? What's that equation? Kinetic energy. So we're talking about the kinetic energy of what? An electron that's getting kicked out. So m must be the mass of the electron.
What's that IO thing again?
Work function.
Work function?
Yeah, we don't know. You have to look it up. Copper, Google it and see what that is. It's going to be some energy. How about V of the electron? So I guess you could put an E on that one too. So look at all the things they can ask you for in this type of photoelectric equation problems, right? More than likely, I guess they could ask you for the work function of that metal, right? But they would have to give you the wavelength of the light that you're shining on it. They would have to give you the mass of an electron, but usually they don't. They just expect you that you're going to look at inside front cover for it. They would have to give you the speed of the electron, and then you calculate work function. Or they could give you work function and ask you for the speed of the electron if they gave you the other stuff. So I think there's a lot of homework on this that we'll be talking about. The wave-particle duality. I think this photoelectric effect is a great representative of this wave-particle duality. Because if you have a solid, right, you have this nice sea of electrons, whatever the theory is there for what's going on in a solid, how the heck can a wave that has really no beginning, no end, how can it kick out an electron? It doesn't, conceptually, it doesn't make sense. But if you took that wave and compressed it into one packet of energy, yeah, now I can see that coming in and bam, right? Because all that energy, it isn't distributed over space anymore. Because I don't see how that could work. That's minute amount of energy distributed over this large length of space, how could that kick out an electron? But if you make it a particle, right? Compress it, comes in, yeah, bam. I could see that kicking out an electron. So light is really confusing. I mean, it behaves to fit the situation. It behaves to fit the observation. It behaves like a particle, in this case, to kick out an electron. If you were talking about diffraction or diffraction, refract, that's all wave properties. That's not a particle. It has to be a wave. So, kind of odd. That's about it. Let's take a look at some of these questions here. So, there's two ways to go about these. We can work on them, right? Get you started and make sure you're comfortable and go on to the next one. Or we can work on it, finish it, and go on to the next one, right? But there's only so many minutes in the period. Work on it, finish it. Because this, whatever we don't complete, is homework. Yeah, this is. Yeah, I typed these out so because no one ever brings their book to class. All right. So. Yeah. So in the back of the book, they call them exercises, and then they call them problems. So, and the problems are usually more involved.
Oh yeah.
So.
Yes, they are.
Okay. So, and with these exercises, here's extra practice, but you don't have to turn them in, right? So what's due the next class period is pretty much the bold words for this, and then these assignments, okay? There's also, do you have articles in here, or did I forget to put the articles in here? I think I looked.
On the back, maybe? I don't know. I didn't look in the back yet.
Yeah, I think I forgot to put articles in here. Oh, no, I didn't. Yeah, they're here. I think they're here. Yeah, in the very back, there's quantum eraser. Oh, no, that's the experiment. Oh, that's an experiment. No, there's no articles in here. Because the challenge of large numbers is what I wanted you to read. But you don't have the article, so don't worry about. Okay, so we'll forget the articles.
I have a question on this book. I just saw on page 18 there, it says chapter 11, B solutions. I don't know what that is.
Okay. I don't know. Okay, so there are, in the back of I think you have, in the back of your book, are all the solutions to these are the exercises. So they have exercises and problems. For exercises, they're divided into A and then Bs. And Bs are identical to the A's, except Bs don't have any answers. The A's have the answers in the back of the book, just numerical. Sometimes there's a hint. So since I'm kind of lazy, sometimes I'll just say, making up an exam, I'll look at, I assigned 2A, so I'm just going to copy 2B and put it on the exam. Because it changes the numbers for me, it changes the stuff for me.
But it's the same way as
So one student, everything evolves, it's the same thing. Everything evolves. So one student asks, hey, can we have the B solutions? So maybe the A solutions maybe the B solutions aren't in the solution manual. Maybe, I don't know. But, they're not? Really? Oh, okay. So that's what these are. These are the B solutions. They're not assigned. It's just to have. I think it's healthy. I mean, it's training. If you want to exercise, right? It's better.
So then these exercises we're only doing A?
So all that's due for the next class period are those bold words and all of these, whatever's assigned.
Oh, that's awesome, because if you have one, you would always make us do B, and B was never in the solutions manual.
Okay. Now this stuff you're going to feel comfortable with. You could probably get away with copying it from the solution manual because the concepts match your current understanding. You're not going to really have any gaps. But when we get further on, if you continue just copying the solution manual, you're going to have to literally memorize how you approached and you're going to have to memorize the solution that seems so ambiguous out of nowhere for a gazillion different problems. And it can be done, but it's tough. So use the solution manual in a tender way, right? Use it as a backup.
Okay, those are the problems that are in the book?
Yeah. And they're also typed out up here.
Okay.
Make sense?
Yeah, I was just looking for it in here, but they're not in here, right?
Yeah, they should be typed up in there, aren't they?
No, the problems aren't like that.
Yeah,
Oh, they're
not
not.
in the,
I gave you the wrong one. Oh.
well,
That's
I mean, they're in the book.
We'll
that's
find
why.
Okay.
That's what I was asking.
So you'll have to bring your book to class then.
Yeah.
Because your entire manual isn't going to have these typed out.
Yeah, that's why I brought mine.
Oh, so you said you made a copy of the manual where all those were all our homework problems?
Well, I have all these work studies, right? And they typed up all these questions for me. But I didn't give you that version. I thought I did. I gave you
Just
the version where they didn't type up all the
Yeah, it's fine, regardless.
So
We're
this
gonna-
book
we're
is
gonna
only
have
worth
to
$25
Yeah.
$65 back.
So you're going to have to bring your book to class. But you can always read it here.
Yeah.
But you don't need to spend time copying this down because this is 11.3 in the back of the book.
So
Okay.
PMT was in which instrument?
It's in the UV Viz,
Okay.
and it's in the fluorimeter, which you guys can't touch.
Oh.
And
Is that a new one?
because you push the wrong button and a $3,000 black puff of smoke comes up the back. Even though it says push this button, then push. And why would someone design an instrument like that in the first place? Push this button, then push that button. It's stupid. Push one button.
We use that one for instrumental, though, right?
We used it. We only use it for research. So it's actually a detector I like it as a detector for the HPLC. There's a scorpion experiment where we scraped all these scorpions and got the fluorescent compound and isolated it. Well, it's only with that fluorimeter we could detect it. So we had everything run to the fluorimeter. It's worked pretty well. Okay. Determine the wavelength of the radiation of the most. So what do we decide? Do you want to work them through, complete it, or you want to jump from problem to problem? Complete it,
Let's do the first one at least.
and just see how it works.
Yeah.
Determine the wavelength of the radiation of the most intense electromagnetic radiation emitted from the surface of the star Sirius, which is a surface temperature of 11,000 Kelvin. Okay, if you wanted to make this here, this is what I'm looking for. At the end of your chapter, if this, I think, would be a good way for you to be handling this. Treat every time you're doing homework as an exam situation. This is all you have to look at. What I did is I scrolled to the back of your chapter. It's a chapter 11 outline, useful integration, trigonometric relations, useful equations. This is what I'm giving you on the exam. So if you're used to using this for each particular homework question, man, the exams would be that much smoother. So I think you should look at this. It's only Pablo's got his book. But it was saying, the question was saying, what is the maximum wavelength, something or other.
Yeah,
right?
the question, yeah.
Determine
Determine the
the
wavelength
equation
of the
T
radiation.
See
lambda
that?
max.
That's it.
'Cause
Right,
look
that's
at
that.
if we want.
Yeah, it is. That's that. Go up to the very beginning, right? That
Wavelength of radiation.
Wien, I'm not sure I pronounced the German guy's name, I think. Displacement law, right? So that's what we're going to be using. That's what I'm saying. If you can almost just tear that page out and be using this in all your homework. Because this is all you're going to be given. On page 12, on my book.
Oh.
Is it-
We don't have that either. Oh, there it is.
Is it page 12?
Page 17.
Yeah, so your numbers are off mine.
Yeah.
Oh, because you have concept preview. Yeah, I don't have that in here. Okay. So they must have gave you T in the problem.
Yep.
And you know what C2 is?
Yep.
Now, what will your okay. Oh, I forgot what it was already.
1/5.
What was it?
C2.
C2, yes.
C2 CMK something or other.
Well, the equation itself is just
C2
C2.
equals HC over K.
T lambda max is 1/5 C2.
Yeah.
Jeez. I'm combining them. All right. All right, you know what the T is? Is the T in the right units?
Yeah.
Yeah.
In Kelvin, right?
Because, yeah, 'cause you got to plug in what C2 was. And that's that 1.44 CMK, is that
Yeah.
right? Okay. So T's in the right units. Lambda max is going to come out in what units?
It's gonna be in centimeters.
It's going to come out in centimeters. Yep. It looks like they don't care, so you just keep it in centimeters or report it, convert it to nanometers if they would have asked for that.
Man, that's a long wavelength.
Well, it makes sense because a star is really, really. Would you expect that wavelength to be in the visible or something? No, you'd expect it to be where all the most of its energy being emitted is. It's going to be in the heat region. So that makes sense. Okay. Did you want to finish it, or you want to go on the next one?
Go on.
Okay. Calculate the power radiated by a 2 by 3 meter section of the surface of a hot body at 1500 Kelvin. So looking at that equation sheet, which I don't have. I can look over here. What equation looks like might make the most sense for that? Calculate the power. And they give you the temperature. Excitance, exactly. Because what you got to remember is excitance is what over what? Power over area. Yeah. For some reason they call that excitance. And if you see the equation, exactly, that's the one you want to use. Right. So where do I write this power over area? What was the sigma? Go down further in that page. I'm pretty sure they give you a number for the sigma. Right? Didn't they somewhere? I didn't give you a number for the sigma? I must have screwed up then. Because if you go back in the notes, for here's the equation we're trying to use, because we said that was power per unit area. That sigma is just right down here.
Oh, okay. I got it.
Right? So it should be on that equation sheet.
Yeah, it is.
Okay. So we know what sigma is. Again, where do you write the power over area, though, to solve for this thing?
Yeah.
Which?
Yeah, it would be the sigma, because like over here,
No.
it has x watts over.
Sigma is that, though. So for sigma, we have to type in 5.67 times 10 to the what?
Negative 8.
-8. What is it? Watts.
Over meter squared times Kelvin to the fourth.
That is my sigma.
Are you looking for
And then the T is what?
Temperature.
And I'll put what into the fourth then?
15,000. I mean, 1500.
Yeah, 1500.
so then your
My M,
power over area would be your M,
because excitance is the M.
right?
So excitance is M, so excitance is power over area. So this is where you write power over area. They want us to calculate the power. That means if we end up doing this thing right, we should end up with what units? What units should we in? Watts. So if we do this right, this joules per second, yeah, but they don't have that in here. They just put it in watts. So everything else should cancel if we do this right. And the kelvins look like they're going to cancel on you. What do you put in for that area?
How does that meter square cancel out?
Well, we're solving for power. Don't you got to get rid of this?
Yeah, you times.
And move it over to the,
Okay. I see it.
right? Don't you have to move the area over to the other side? Yeah. So bring it over here. And that's, how do you calculate the area?
2 meters by
2 meters times 3 meters.
6 meters squared.
Yeah. There's how my meter squares will cancel out. Okay. We're about out of time.
It
But
isn't so bad.
no, they're not too bad.